Well, welcome back. This is Unit 4.2, and we're continuing our discussion on gases, Chapter 14 in the book. We're going to specifically be talking in 4.2 about vapor pressure of water. John Dalton, who is an English chemist, found that water in a closed container will gain enough energy to vaporize. And remember, water vapor is a gas. So when the vapor pressure of a substance reaches the atmospheric pressure, then the substance boils. And vapor pressure depends on two things: the chemical structure and the temperature of the substance. Well, all in all, different molecules are held together by stronger or weaker intermolecular forces. So that's the forces between the molecules. And that's what holds them in the liquid state. So boiling points are different for different molecules because they have different energies or different forces that are holding them together in the liquid state. For example, diethyl ether has a boiling point that's really close to human body temperature. So when it reaches that temperature, then it vaporizes. And we've all had experience with isopropyl alcohol, that's rubbing alcohol. So if you take rubbing alcohol, like if you're going to get a shot or an injection or something, and the nurse rubs that alcohol on your skin, what does that feel like? Well, it feels cold. And the reason for that is because the alcohol is moving from the liquid state to the vapor state. And so it's breaking those intermolecular bonds that are between the individual molecules. And when you break bonds, it takes energy to do that. So they absorb that energy from your skin. So your skin feels cold because it's losing that energy. All right, and partial pressure. Dalton also developed the law of partial pressure, which says that the pressure of gas A plus the pressure of gas B plus the pressure of gas C, et cetera, equals the total pressure of the gas mixture. So written mathematically, that's PA plus PB plus PC equals the total pressure. So say, for example, we knew the pressure of neon gas was 0.5 atmospheres, and we mixed it with helium gas that was a 0.5 atmospheres. Then the total pressure of that gas is going to be 1 atmosphere. You just add those together. Okay. So let's examine the diagram that's here on the right. We have 3 gases, and assume that all 3 valves are closed for the time being. Okay. And when we open these valves, then the gas diffuses and it creates a different volume of gas. So the question here says, assume that all 3 valves of the gas are open at the same time so they can diffuse through this system and reach an equilibrium. What is the total pressure of the system? All right, so in order to do this, to get this solved, we have to consider each gas separately. So we see our helium gas here is 1 liter at 150 kPa. And we have our neon gas, we have 1 liter, that's at 90 kPa. And we have argon, 2 liters at 325.0 kPa. So what is the volume of the helium when all the valves are opened? All right, so to do this, we have to reflect the change in the volume and the pressure. So what is the formula for volume and pressure? Well, that's going to be P1 V1 is equal to P2 V2, because we have a pressure and a volume in an initial state when this valve is closed right here. And then we have, when the valves are open, we have a different pressure that we're looking for and a different volume. So let's look at just helium. So if we take helium, the pressure initially is 150.0 kPa. And the volume initially is 1. Okay, that's going to be equal to, what we're trying to find is P2. So V2 When these are all open, this is 1 liter plus 1 liter plus 2 liters. So that's a total of 4 liters times P2, and let's just call this X. Okay? So 150 times 1 is 150.0, and that's equal to 4X. All right? So if we solve for X here, we just had to take 150 and divide that by 4. We're going to get 37.5. So X is equal to 37.5 kPa. All right, so that's for helium. Now, if we do the same thing with, let me write this down, 37.5 kPa. If we do the same thing here for the neon, well, instead of 150, let's just substitute in 90 because it's 1 liter. So that's going to be 90 divided by 4. That's going to give us 22.5. Okay, and finally argon. Now we're going to have to do 2 here and 325. So if we take 325 times 2, then we're going to divide that by 4. We're going to get 162.5. So this is the pressure of the helium after. This is the pressure of the neon after. And this is the pressure of the argon after. Now remember, Dalton said all we have to do to get the total pressure is just to add these up. So we have 37.5 plus 22.5 plus 162.5. That's going to give us a total pressure of, let's see, how many sig figs do we need? 333. All right, so 223 kPa is our total pressure. All right, so we just have to use the before and the after for each one of these gases and then add it up. Okay, a student performs an experiment in which she prepares hydrogen gas by reacting hydrochloric acid and zinc metal. Okay, so she's going to take hydrochloric acid, which is HCl, plus zinc metal. Okay, and this is going to give us zinc chloride plus hydrogen gas. Okay. After collecting 250 milliliters of gas, so we have 250 milliliters of this gas, by displacement of water from a gas collection jar over a pneumatic trough. All right, so what does that mean? That means that we have a jar. I'm just going to draw this real rough. That's submerged in water right here. And then we have this tube that comes out like this. That's connected to a reaction flask like this. So the hydrochloric acid and the zinc are put in here and mixed, and there's a rubber stopper here in this. And as these react, it releases this gas. And so to collect this gas, we have to do it by collecting it over water so that the gas can come up here, but it can't escape because the water is holding it in. We have this inverted. It's like putting a glass upside down in water, or, you know, those diving bells that they used to use. They have oxygen here, but the oxygen can't get out because it can't go past the water. So that's exactly what's happening. So she's collecting the gas in this over this trough. The student equilibrates the system to an atmospheric pressure of 99.2 kPa and the lab temperature of 24 degrees Celsius. Okay, so this is a pressure and this is a temperature. Eliminate the vapor pressure of the water, which is 2.98 kPa. Now, what is the mass of the hydrogen that she has collected? So we're looking for a mass of hydrogen. hydrogen gas. All right, so let's look at this. So when you collect this gas over this pneumatic trough, not only is there hydrogen gas in there, but there's also water vapor, because this water here is gaining enough energy to go to a gas. So we have a mixture of hydrogen gas plus water vapor. Okay. So we just want to know about the hydrogen gas. So we need to eliminate the water vapor. And the only way you know that is by being given that. So at a certain temperature, then there's a certain pressure of water vapor, and it gives us that in here. So at 24 degrees Celsius, we have a water vapor pressure of 2.98. And we're going to do a lab where we do this. And so what we're going to have to do is eliminate this water vapor pressure right here from the total pressure. All right. And they said here that she equilibrates it to 99.2. So we're going to take our 99.2 kPa, and we're going to subtract out that water vapor pressure of 2.98 kPa to get just the pressure of the hydrogen gas. Okay, so calculators, 99.2 minus 2.98. That's going to give us 96.22. Okay, and that's just the pressure of the hydrogen gas. All right, and so now we need to ultimately answer this question: what is the mass of hydrogen? Well, we have pressure, the new pressure right here of just the hydrogen gas. We have the temperature that it's collected at, and we have the volume of the gas right here. So we can use PV equals nRT to solve for moles, and then we can convert our moles into mass using the mole map. All right, so let's do that. So moles is going to be equal to pressure volume over RT. So our pressure, 96.22 kPa, okay, times the volume, which is in liters. Remember, it has to be in liters, so this is a 0.250, divided by our R. So we need a gas constant, and this gas constant is 4 kPa, because our pressures are all in kPa. So that's going to be 8.31 times our temperature, and the temperature has to be in Kelvin, and this is collected at 24 degrees Celsius. So for Kelvin, that's 273 plus 24, so it's going to be 297. Okay, so let's grab our calculators. 96.22 times 0.250 divided by 8.31 times 297. We're going to get 0.009746481 moles. But that's not what the question is asking. It's asking for a mass. So we're going to have to convert this. So we want to get rid of moles, put it on bottom. We want to change it to grams. Grams per mole is a molar mass. So for 1 mole of hydrogen gas, remember it's H2. Okay, so that's going to be 2.02. 2.02. So we need to multiply what we got on our calculator by 2.02. We're going to get 0.019687. How many sig figs do we need? Let's see, here's 2. So leading zeros never count. So 1, 2. So this 6 tells us we round the 9. Well, that 9 is going to round up to 10. So that's going to round this number here to a 2. So it's 0.020 grams for our final answer. All right, so derived formulas for partial pressure. Well, we can use algebra and the ideal gas laws to calculate the partial pressures of each gas present in a mixture. So if we take P total times V, PV equals nRT, and this is the total, N total RT. And remember that a percent is a part of a whole. So we're going to make this as a percent. So if we take just the partial, the gas, like gas A, PV equals nRT, and it's the moles of this gas, over P total V equals N total RT. And then we eliminate what we have, because what's on top cancels what's on bottom, right? And we're going to end up with PA is equal to NA, and then P total equal N total. So we have PA over P total is equal to NA over P total. And if we rearrange to solve for PA, then we have P total times NA over N total. And this right here, part of a mole over the total moles, is what we call a mole fraction. It's a fraction of a mole. So if we take the mole fraction, or the fraction of a mole, multiply it by the total pressure, then that's going to give us the pressure of the gas. Okay, so let's look at this applied. So we have a problem that says a technician injects 7.50 grams of liquid nitrogen into a sealed glass tube filled with 12 grams of neon gas. The nitrogen vaporizes and fills the container for a total pressure of 1.4 atmospheres. What is the partial pressure of each gas? All right, so if we have 7.50 grams of liquid nitrogen, and here we have 12.0 grams of neon gas, and we have a total pressure of 1.40 atmospheres. Somebody's mowing their lawn. Sorry, you can hear that. I don't have a soundproof room. So if we use the formula that we had, which is the partial pressure of gas A is equal to the total pressure times the mole fraction. So it's going to be NA over N total. Okay, then we can get the pressure of each gas. So what we have to do here is find the moles of each gas. So if we have 7.50 grams of nitrogen gas, we need to change that to moles. So grams are on the bottom, moles on the top. So 1 mole of nitrogen gas, well, if each nitrogen is 14.01, then 2 is going to be 28.02. Okay? And so grams is going to cancel, leaving you moles. Now we're going to do the same thing here, because we had to have the moles of this one as well. So grams on bottom, moles on top. 1 mole of neon is 20.18 grams. Grams cancels, leaving you with the moles. All right, so let's go ahead and do the math on this one. 7.50 divided by 28.02 is going to give us, we don't need all of those numbers, so let's look and see. We are going to have 3 sig figs in this. So if we just use 5, so 0.26767 moles. Okay. All right, let's do the other one. 12.0 divided by 20.18. Okay, and we're going to get 0.5946 moles of neon. All right, so we need to have a total moles, so we're going to add these together. All right, so 0.26767 plus 0.59465, we're going to get 0.86232 is going to be total. All right, so now To get the pressure of each gas, we're going to take the total pressure, which is 1.4 atmospheres, times the mole fraction. So we're going to do for nitrogen first, so 0.26767 divided by 0.86232. Okay, and that's going to give us the partial pressure of just the neon gas. Okay, and I'm going to draw a line here. So we're going to do the same thing here, 1.40 times the mole fraction. Well, this is 0.59465 over the total 0.86232. Okay. So let's multiply both of these out. So 0.26767 divided by 0.86232 times 1.4. That's going to give us a partial pressure. I'm just going to write pressure A of 0.43457 atmospheres. Okay. And then the same thing with the neon gas, 0.59465 divided by 0.86232 times 1.4. That's going to give us 0.96543 atmospheres. So that's PB. Okay? So this is the pressure of the nitrogen gas. This is the pressure of the neon gas. All right, now if you want to check yourself, you can add these two back together and see if you get 1.4. So 0.43457 plus 0.96543, and it equals 1.4 atmospheres. Okay. All right. So I apologize again for the sound of the mowers mowing the lawn, but that's it for this notes on vapor pressure 4.2. So make sure you slap that like button right across the face, subscribe, give me a thumbs up, and leave me some comments.